Welcome back. This is the last part of our lecture on vaccination. So in fact, this is going to be part three of three. We have discussed in explicit detail here very basic model that incorporates vaccination. And the most important thing is we talk about a model with three compartments like that, and then we did some mathematics to convert that model into two equations instead of two compartments instead of three, and also by doing rescaling and by redefining a new time variable, we were able to convert this into a form that has no dimension. This is the so-called dimensionless form of the model. Parameters here that are very important. There is this very important parameter we call the basic reproductive number, R naught. This F denotes the ratio of the infectious period over the life expectancy, and P, this parameter P, has to do with vaccination coverage, right? If you're covering 10% of the population, 50%, 100%, and so on, right? So P is a number between 0 and 1. So what we'd like to do next is to code up, write some computer code in RStudio and compute some numerical solutions. So let's do that. Let's switch gears here. We go to RStudio. I'll show you first what this code looks like. The most important part of this code is this portion here where on line 30 we define the function that contains the equation, the expressions for the equations, right? There are three parameters, R0, F, and the parameter P. And then after we have defined that function, there is a call here in the code. The code is invoking ELSORA. Remember that for this to function, you have to make sure that you have already installed that package that's called desolve. Okay, so let's see with these values, with those values, we are now simulating this with values of R0 being extremely small, extremely less than 1, 0.07, and then F has a value that's also very small, and P has a larger value, 0.7. Okay, so what happens if we use these values? Let me shrink this. This is a code here with maybe 60 lines of code. I'm going to highlight everything and then I hit run, and this is going to produce an output. So let's look at this output here. We're seeing the values, the numerical values of x of t and y of t. X of t is denoted in blue, y of t is denoted in red, and for this case in which R0 is less than 1, then y of t tends to 0. So here we gave initial conditions. That are both starting at 0.5. Okay, and you can see that in this case, when R0 is less than 1, then the population of infected individuals is dying off to 0. It approaches 0 rather fast. Remember here the time is tau, because this is the non-dimension, the model that has no dimensions, right? So let's do now a simulation. This is basically the same script here. Again, the most important part is where we define the equations, right? And in this, this is not presented here in two scripts. You could have one script and just reset the values for the parameters, but let's see what we have here with these values. Then R0 now has a value of 7. F has a value, basically the same value, and P still has the same coverage value. Okay, so I'm going to shrink this window here, and I will highlight that script and then hit run. This will be executing that script, and look how beautiful this simulation is coming up. The red curve, the initial conditions are different now. Okay, before we had initialized almost at half, 0.5 were susceptible, 0.5 were infected, and the infected with R0 less than 1 were dying off to 0. Here, the initial conditions, let's take a look. Which variable is stored in initial conditions? Is this y init? And you can see that x of t is initialized at 0.999, while y of t is initialized at 0.001. Okay, and that explains why this red curve, y of t, it's initializing at a low value, at a value that's basically infinitesimal, okay? And it rises from that low value to all the way here to a maximum value that's close to 0.6, right? Remember, this is now a fraction of the population, right? And basically by doing so, then it attains its maximum and then it decays close to 0. Most of the population was initialized to be susceptible, and then you can see how that fraction drops drastically, right? So this is a simulation or a numerical solution of that SIR model with vaccination. Okay, so it was an SIR model with vaccination with birth and death processes, and also it was a reduced model, and it was rescaled, and it was non-dimensionalized. So this is the dimensionless version of the SIR model with vaccination. Okay, and this concludes our discussions on a basic mathematical model with vaccination.